In this video, we're going to look at a problem of input-output analysis, and this is for a small economy that has a merchant, a baker, and a farmer. So all of the input requirements are given in this paragraph, and I am going to start forming the input-output matrix as I read. We have the three sectors, which are the merchant, the baker, and the farmer, and I'll give each one of those a column. Although those labels aren't part of my matrix, I'll just put them up there so you can see what we're doing. For each $1 of output, the merchant requires 30 cents of baked goods and 40 cents worth of the farmer's products. So it doesn't require anything of its own, but it requires 30 cents worth of baked goods and 40 cents worth of the farmer's good. To produce $1 of output, the baker requires 50 cents worth of goods from the merchant. So that's 50 cents worth from the merchant, 10 cents worth of its own goods, and 30 cents worth of the farmer's goods. So they're always coming in that order. The first row is for the merchant, second row for the baker, third row for the farmer. The farmer, to produce $1 worth of output, he requires 30 cents worth of goods from the merchant, 20 cents worth of goods from the baker, and 30 cents worth of his own goods. So there's the input-output matrix, and the demand matrix is coming from consumer demand. The question is, how much should each produce to meet consumer demand of $20,000 worth of output from the merchant, $15,000 worth of goods from the baker, and $18,000 worth of goods from the farmer. So instead of putting those large numbers, I'll just go with 20, 15, and 18, and that's going to be in thousands. So that's what the consumers want, but we know that they have to produce more than just the consumer demand because they need to make products for each other. Okay, let's take a look at why I put that input-output matrix together like that and how we're going to come up with a solution to the matrix equation. First of all, let X be the total output for the merchant, Y is the total output for the baker, and Z the total output for the farmer. And of course, these are what we're trying to find. So let me write a system of equations that models this situation. X, the total output from the merchant, where does it go? Well, none goes to himself. So for each $1 of output, he doesn't want any of his own goods. But 50 cents times the total output from the baker, and 30 cents for each $1 of output from the farmer, that's Z, plus 20,000 goes to consumers. So here we have where all of the output from the merchant goes. Part goes to the baker, part goes to the farmer, part goes to consumers. Now, Y, which is the total output for the baker, 30 cents for each $1 of output goes to the merchant, 10 cents for each $1 of output goes to the baker, and 20 cents for each $1 of output, that's Z, goes to the farmer, and 15,000 goes out to consumers. Total output for the farmer, 40 cents for each $1 of output for the merchant, 30 cents for each dollar of output for the baker, which is Y, and 30 cents for each dollar of output for the farmer, plus 18,000 for the consumers. So that system of equations in red is what I'm going to need to solve. I'm going to write a matrix equation that shows that x, y, z, those are my variables, and I'll pack them in a matrix. I have the coefficients, which is my matrix A, the input-output matrix that I formed right out in the beginning there. Here's why it looks like that, times x, y, z, plus the demand matrix, which looks like that. So this matrix equation in green says exactly what those system of equations says in red. You can see across the top equation, x is equal to 0 times x plus 0.5 times y plus 0.3 times z plus 20. Next, 0.3 times x plus 0.1 times y plus 0.2 times z plus 15. And z is equal to 0.4 times x plus 0.3 times y plus 0.3 times z plus 18. So this matrix equation says exactly what the system says. And if I just give letters now to these matrices, A is the input-output, and that's times x again, plus the demand. To solve this equation, I'm going to get the variable matrix together on the left. I'm going to factor out the x in hopes of getting it alone, and I'll multiply by the inverse of I minus A, and there I have my solution. So every input-output analysis problem will have this as the solution. I have my matrix A here and my demand matrix here. And for these two, I want to calculate I minus A inverse times D. And I'm going to go to MATLAB to do that. So here I am in MATLAB, and I'll type in A, the input-output matrix, 0, 0.5, 0.3, 0.3, 0.1, 0.2, 0.4, 0.3, 0.3. Whoops, and end the matrix. The demand matrix D is 20. I end that row, 15, end that row, and 18. So the solution, if you look back, is I minus A inverse times D. And I'm going to type that in one command. The inverse of I now is the identity, the 3 by 3 identity. So I have to type it in like that, EYE of 3. That tells MATLAB which size identity. I minus the matrix A, and I'm going to calculate the inverse of that, and I'm going to multiply by D. And there it is. I have my solution to the input-output problem. It is $85,034.50, 68,000, and 103,448.30. And I can take that and just copy it and put it back on my screen right here. Hopefully it's not going to be too small. And this is going to be in thousands. So I have 85,034.50. That's from the merchant. I have $68,000 of output from the baker and $103,000, 448.30 from the farmer. And that's going to be how much is needed to meet the consumer demand of 20,000 from the merchant, 15,000 from the baker, and 18 from the farmer.